In this video, we're going to talk about another method for numerical integration. In particular, we're going to talk about Romberg's method. So to discuss Romberg's method for integration, we must first introduce Richardson Extrapolation. Richardson Extrapolation is a powerful method that combines two or more less accurate numerical solutions to obtain a highly accurate solution. When this method is applied to the Trapezoidal Rule for numerical integration, the technique is called Romberg's method. The essential ingredient of Richardson Extrapolation is the knowledge of the order of the truncation error. So let's assume we have a quantity A, and we're going to use a numerical technique to approximate the value of A by choosing the value of H1 and calculating an estimate, which is denoted A star as a function of H1, according to the equation here. So A is the quantity we're interested in, A star of H1 is our estimate, and the difference between the estimate and the actual value is given by this error term, which is a constant times H1 to the power K1 plus some other term, so another could be constant, directly proportional to H1 to the power K2. So C is a constant whose value does not need to be known, and here K2 is greater than or equal to K1 plus 1. So K2 is larger than K1. Now if we take another estimate for A using a smaller h, so H2 is less than H1, and where the ratio of H1 over H2 is equal to T, then the new estimate for A is A star as a function of H2 according to the equation here. So again, we have A is equal to the estimate A star of H2 plus this error term, which is a constant times h to the power K1 plus order h to the power K2. So if we multiply the second equation by t to the power K1 and subtract the first equation, we get the expression shown here. So basically we've eliminated the h to the power K1 terms by taking a linear combination of those two equations. And this can be rearranged to show as shown here. So this gives us a new estimate for our quantity A that is now order h to the power K2. So it's a higher accuracy than the previous one. And this was achieved by combining two estimates that were of order h to the power K1, and then we were able to achieve a higher accuracy estimate by combining those two lower accuracy estimates. So in other words, the first error term in a method is directly proportional to hk1. Then by combining two values of h, we can get an estimate whose error term is directly proportional to h to the power K2. And this equation can also be written as shown here. Basically, all we've done here is replace the h over 2 with, the h2 with h1 over t. And this is known as the Richardson Extrapolation equation. And this can be applied to lots of different numerical techniques. So if we suppose the trapezoidal integration scheme is applied for a particular value of h1, we know from section 11.3 that the truncation error in the trapezoidal rule is order h2. Therefore, K1 is equal to 2. If the trapezoidal rule is applied again with half the step size, so t in this case is h1 over h2 is equal to 2, then substituting the equation in the previous slide yields the expression shown here. So it was t, which is 2, to the power of K1, which is also 2, multiplied by our higher accuracy estimate, which is it with the step size of h1 over 2, minus our lower accuracy estimate, which is it of with the step size of h1, divided by t to the power of K1 again, minus 1. And this the order of this is now h to the power of K2. So this is equal to 4 it h1 over 2. So 4 times our higher accuracy estimate minus 1 times our lower accuracy estimate divided by 3 gives us our estimate that is even higher order accuracy, so h to the power k2. So for the trapezoidal rule, k2 is equal to 4, so the error term using this method is now h to the power 4. So combining just with a linear combination of two estimates that were h to the power 2, we were able to get an estimate that is h to the power 4. And this method can be applied successively by halving the value of h to obtain an error estimate that is h to the power 6. So if we assume that the trapezoidal integration is available for all of these step sizes, so h over 2, h over 4, and h over 8, then the first two cases can be combined to find an estimate that is order h to the power 4, which we just saw. The last two can also be used to find an estimate that is also order h to the power 4, where h in this case is h1 over 4. And then we can apply the Richardson extrapolation equation by basically getting a linear combination of the two of these, and in this case t is equal to 4, to produce this estimate for I, which you can see is now equal to 16 times the second estimate minus the first estimate divided by 15. And now this estimate is order h to the power 6. So by a linear combination of two fourth order estimates, we were able to get a sixth order estimate for our integral. And this process can be extended even further to find an estimate that is order h8. And in general, the process can be written as shown here. So we've got this, it's denoted I, j, comma, k is equal to this linear combination of our higher order, lower or higher accuracy estimate, so with the smaller step size, minus the lower accuracy estimate divided by 2 to the power of 2k minus 1 minus 1. And then this gives us an estimate that is order of h2k. So this is called the Richardson extrapolation for the trapezoidal rule, which is known as Romberg's method. And so here j plus 1 indicates the more accurate integral, so that's this one here. J indicates the less accurate integral, so that's this one here. The k's correspond to the calculations with the error terms of h squared, h to the 4, h to the 6, etc. And this equation is applied for k is greater than or equal to 2. And we'll see kind of how this works in a couple of examples. So typically the Romberg's method is done schematically in a table. So this table demonstrates how the process is applied to obtain an estimate that is order h10 using this algorithm. So the first column here corresponds to evaluating the integral for values of h is this one, and then h over 2 will go here, h over 4, h over 8, and h over 16. So these correspond to n, 2n, 4n, 8n, 16n trapezoids, respectively. And then the equation on the previous slide is used to fill in the remaining values in the table. So we can use the trapezoid rule with h over 2 to get our estimate I21. And then we can take a linear combination of these two. So using that equation, it's 4 times I21 minus I11 divided by 3, which is now fourth order accurate. Then in the next iteration, we can add one more estimate of our, using the trapezoid rule with h over 4. And then we can combine these two with this linear combination to get another estimate that's h to the power 4. And then we can combine these two fourth order estimates to get a sixth order estimate, where here the linear combination is 16 times the higher one minus 1 times the lower one divided by 15. Then in the next iteration, we add another estimate using the trapezoidal rule with a step size of h over 8. Then we take the two second order estimates to get another fourth order estimate. And then we can take these two fourth order estimates to get another sixth order estimate. And then we can take our two 6th order estimates to get an 8th order estimate. So here the linear combination is 64 I23 minus I13 divided by 63. And then in the next iteration, we can add another estimate using the trapezoidal rule with a step size of h over 16. We can combine these two to get a 4th order estimate. Then we can combine our two 4th order estimates to get a 6th order estimate. And then we can combine our two 6th order estimates to get another 8th order estimate. And then finally, we combine our two 8th order estimates to get a 10th order estimate. So here the linear combination is 265 or 256 times I24 minus I14 divided by 255. So in a typical implementation of Romberg's method, the error tolerance epsilon s is specified and the algorithm uses Richardson extrapolation as many times as necessary to achieve the prescribed error. So the stopping criterion for this algorithm can be set as the relative error, which is IIk minus IIk minus 1 divided by IIk less than or equal to epsilon s. So basically this takes the values in the top row of our Romberg table with the sort of the last one minus the one before it divided by the last one. So let's do an example. So in example 11.3 from section 11.3, the trapezoidal rule was used to find an estimate for the integral of f of x is equal to e to the power x on the interval from 0 to 2. And we found that when 71 trapezoids were used, an estimate of the integral was 6.38948 with an absolute error of 0.00042. So now we want to use Romberg's method to find the depth k, starting with h is equal to b minus a, which is 2, so that the estimate for the same integral has the same or less absolute error. So we want to find the number of the depth of the table k that we need to be able to get our true error, or the absolute error, less than 0.00042. And then we can compare the number of computations required by Romberg's method to that required by the traditional trapezoidal rule to obtain an estimate with the same absolute error. So we'll basically compare the computational efficiency of the two different methods. So first, we're going to start with k equals 2. So for that, we need to compute the integral numerically using the trapezoidal rule for a chosen h, and then for h over 2, to fill the entries I11 and I21 in the Romberg's method table. So if our first h is equal to 2, then that means we need one trapezoid to cover the whole interval. This is our estimate using the implementation of the trapezoidal rule with h is equal to 2. So for that, our estimate is given as shown here. Then if we half the step size, so now we've got h is going to equal 1. So we have two trapezoids. This, and we just plug in to our trapezoidal formulation. Our estimate for the integral I21 is equal to 6.91281. So using the Romberg method, the value of I12 can be computed as this linear combination of our second order estimates. So I12 is equal to 4 I21 minus I11 over 3. So it's 4 times the more accurate integral minus the less accurate integral divided by 3. So just plugging in the numbers, we get that I12 is equal to 6.42073. which has a corresponding absolute error as shown here. So it's important to note that this is the exact value because we're using the absolute true error here. So we're comparing with the exact value. So we see that our error is 0.0317, which is greater than our prescribed accuracy of 0.00042. So this is what it looks like in the table here. So what we've done is use the trapezoidal rule to calculate this value when h is equal to 2. And then we used it to calculate this value when h was half of that, so it was 1. And then we used a linear combination of these two to find this estimate here. So next we need to fill the table to the depth of k equals 3 To do that, we need the value of I31. So this corresponds to calculating the trapezoidal rule with a step size of h over 4. So 4 trapezoids will be used on the whole interval. So just implementing the trapezoidal rule with 4 trapezoids, we get that our estimate is equal to 6.52161. And the remaining values in the Romberg table can be calculated as shown here. So I22 is the linear combination of I31 and I21, which is equal to the value shown here. And then I13 is equal to the combination of our two fourth order estimates. So 16 I22 minus I12 over 15, which is equal to the value shown here. So this is what it looks like in the table. So what we've done is added another estimate using the trapezoidal rule with h over 4, and then used a linear combination of these two to find another fourth order estimate, and then a linear combination of these two to find our sixth order estimate. And so we can calculate the absolute error here, which is less than our specified error. So the error with this estimate is 0.000189. And I posted a MATLAB script that performs this, and this is the output using that. So the estimate of the integral is 6.3892 after 3 iterations. So let's take a look at the number of computations required here. So for the same error, the traditional trapezoidal rule would have required 71 trapezoids. So if we assume each trapezoid is 1 computation, then the Romberg's method requires computations of 1 trapezoid for I11, 2 trapezoids for I21, and 4 trapezoids for I31. So this gives us a total of 7 trapezoids worth of computations. So this is almost 1/10 of the computational resources required by the Romberg's method for this example to produce the same level of accuracy as using the traditional trapezoidal rule. So let's take a look at another example. Consider the integral shown here. We want to use the trapezoidal rule to draw a table with the following columns using n is equal to 1, 2, 4, 8, 16, etc. up to 128. We want to find for each of those n as prescribed, h, which is the width of each trapezoid, it is the estimate using the trapezoidal rule, I true is the true value of the integral, so that would be the same for all of the rows, and then the absolute value of the true error. And then we want to provide the Romberg table with a depth of k equals 5 and compare the number of computations in each as well as the level of accuracy. So the true value of the integral can be computed using the built-in MATLAB function, which of course is a numerical approximation, but it is a good enough approximation to the true value. So the true value of this integral is 6.69331. So the table here shows that with 128 subdivisions using the trapezoidal rule, the value of the absolute error is 0.00011. So this table was produced using MATLAB script using the implementation of the traditional trapezoidal rule. And this shows the Romberg table with a depth of 5 as well as the corresponding error estimates. So you can compare the results and see how powerful the Romberg method is. So the Romberg table uses only the first 5 entries, so up to n equals 16 of the traditional trapezoidal rule method, and then just uses a few calculations to combine these estimates according to the Richardson extrapolation. And by doing this, Romberg's method produces a value with an absolute error of 0.0000799, which is less than the trapezoidal rule with n is equal to 128. So using a lot less computations, we're able to get a much higher accuracy.